Today we're going to look at some word problems with exponents. And sometimes these topics go back to topics that we've done in the past. So surface area and volume. It tells us that the side lengths of this cube are 4 centimeters. Sometimes if I get a question like this on a test or a quiz or in homework, I would take my paper and the first thing I would do is I would label my different sides because I've read it in my question, but it's nice to see it on the picture as well. And then this question is asking us to find two different things. It's asking us to find the surface area, which I underlined in green, and the volume, which I've underlined in purple. The reason I did them in different colors is so that when I do my work, I'm going to do my work in green when I'm working on my surface area, and my work in purple when I'm working on volume. So surface area was listed first. So in order to be organized, I'm going to write out surface area. Now, what is surface area? What is area? Remember, area is a two-dimensional thing that covers a space. And so we're really looking at this space here, this square here, but on a cube, how many sides are there going to be that have squares? Like if it was a cardboard box and you cut it open and opened it up, you would see that there would be 6 sides. Sometimes with a surface area question, it's nice to like, oh, I'm going to open it up and see what it looks like. If you opened up that cardboard box, can you visualize that would be what it looks like when it's all flat? It looks like the letter T. And if each of the sides is 4, then one square, how do we find the area of a square? And again, on your exam, you're going to have your formula sheet. So a lot of these formulas are on there, but I think some of you might have the formula for a square and the area of a square memorized. Sorry? No, not quite sure. The area, okay. If you've forgotten, then I'm not going to tell you, but I'm going to show you a way that you can figure it out. If you've got it right now, I'm going to just hold it, okay? If it was 4 this way, 1, 2, 3, 4, and 4 this way, 1, 2, 3, 4, and you separated that up, here, I'll draw straight lines. If I separated that up into sections, how many little squares cover the whole thing? 16. That's going to be the area of one of these squares, 16. All area is length times width. So if you wanted to write out here underneath area of one square, and it's not a bad idea to write out the formula from your formula sheet, area is length times width. Well, both the length and the width are both 4, 16, and when we write area, they're centimeters squared because you're counting how many squares does it take to cover the whole thing. So if we know the area of one square, we can figure out the total surface area. Does it make sense that you have 1, 2, 3, 4, 5, 6 of those squares? And each one is 16? So we can just 6 times 16, take out our calculator, figure that out, and we would get 96 centimeters squared. Next, we're going to do volume. I'm going to, oops. Things are having issues on my computer right now. It turned bright because the whole thing There we go. Next, we want to find the volume. For the volume, you've got a formula on your formula sheet. On your formula sheet, volume of a cube or rectangular prism, length times width times height. So you have 4 times 4 times 4. And you get 64 centimeters cubed. Now, the question is, why is this part of our exponents unit? We've got our centimeters cubed, so we've got an exponent there. Can you see that you could have written 4 times 4 times 4 as 4 cubed, because it's repeated multiplication? So when you're dealing with a volume, often you have things cubed. Okay? And when you're dealing with our area, can you see right here, we could have had 4 squared, and our areas are squared units, so we have exponents showing there as well. Working with formulas some more. So we got a couple of fancy. You just have a square on yours? The circle didn't show up? Oh. Or maybe the circle was drawn in the same color. Sorry about that. Okay. Well, I'll get you to redraw this then. When it says inscribed, that means that that circle is touching the edges. The circle is touching the edges of that square. The side length is 20 centimeters. We want to find the area that's shaded. So we're going to brainstorm to begin with. In brainstorming, what formulas or what shapes do you see? You see a circle? No, they're not quite triangles. They kind of look like triangles. So you're saying the shapes that you see are circle and a square. Okay? And we want to find the area. Do we have an area formula for circles? Yes. What is it? Ooh, this will be my one that you don't remember from your formula sheet. Pi r squared. And your area of your square? We just did that one, length times width. So now we have to think, how could we do this area that's left? Okay? Now, you guys know that my weakness is always chocolate, and I always do chocolate bar examples. Okay? So I have a chocolate bar like this, 10 pieces. Okay? Because I like chocolate bars. I take a bite, and I eat 2 pieces. How many pieces are left? Okay? I have a chocolate bar with 10 pieces. I take a bite, I eat 2 pieces. How many are left? 8. How did you figure that out? You counted how much are left? Okay. Did anybody subtract? Yeah. Okay. Now I have a chocolate bar that is a square, and somehow miraculously I put my mouth over top of this square and take a bite in a perfect circle right in the middle. This would be very difficult to do, but I have a chocolate bar that's a perfect square, and I go oh, right in the middle and take out a perfect circle bite. This took years to practice. How much chocolate is left? Does it make sense that if we figure out the area of the square and we figure out the area of the circle and then just subtract it? Okay? So my area of my square, and then subtract my area of my circle, that should give me how much is left. Well, how do we figure out the area of the square? It told us the side length is 20. We should have probably labeled these side lengths right away. So for my square, I need length and width. Do I have that? Yes. So my square is going to be 20 times 20. My area of my circle. What do I need in my circle formula? Pi, well that's a number. I can write that down. I need a radius squared. What is the radius? The radius is 10. Remember, radius goes from the center out to the outside. If we know all the way across is 20, the radius is going to be 10. So it's going to be pi times 10 squared. Again, there we have our exponent. At this point, we can go to our calculator. 20 times 20 minus pi times 10 squared. And we're left with 85.84. It's an area question, centimeters squared. First of all, if this was a chocolate bar that was 20 centimeters by 20 centimeters, let's imagine it. That's about 20 centimeters by 20 centimeters. That's a big chocolate bar. And I managed to take out one bite in a perfect circle in the middle. Okay. Just for the record, it is very hard to take bites out of the middle of chocolate bars in perfect circles. Ooh, excellent. Someone said, I see a right-angled triangle. What do you know about right-angled triangles? Look at all those exponents in that formula. Okay. Now, if you do this, you'll be able to find out this side right here. But the question is that side A, B, or C? Oh, I love that. Someone says that's B, another person says that's A, another person says that's C. We have to make sure we know which one it is, for sure. It is, this is always your hypotenuse. Always the longest side is the C squared. So hypotenuse is the one opposite of the 90 degree. It's always the longest side. This side would be C. So then I can plug in 5 squared plus 12 squared equals C squared. Plug this into your calculator, you're going to get 169. Do you know how to get rid of a squared on your calculator? What's the opposite of squaring? Square rooting. So what's going to happen here is on your calculator, you would have to square root both sides. When you square root both sides, 13. So C is equal to 13. And this is a square. How do we find the area of that square? Length times width. 13 times 13 is 169. So one of the applications of exponents is in area and volume questions. Did we have any units in this question? No. So I was just checking to make sure we didn't have to write centimeters squared at the end, but this question didn't have any units. Sometimes you might even get some teachers sometimes say, well, if there's no units, write units squared. You can do that if you want, but I figure if the teacher didn't write units and you didn't write units, it's kind of mean for them to take off marks. Another application of exponents that we're going to look at is in biology. I'm going to make this a little bit bigger so we can see. Yes. Well, the problem is the science and math and a whole bunch of things, they start to interconnect. Did you ever do any bacteria experiments in science? You ever do any bacteria experiments in your lunch kit, in your room? Yes? Or in your locker? So, if you left that cookie in your locker for till the end of the year and then tried to eat it, you might have a bacteria experiment on your head. Okay. So what does the growth of bacteria is caused by cells splitting in half. Okay? So a cell divides, you had one, now you have two. If both of them split again, then you would have 4. If both of them split again, then you would have 8. And so here is an example. This is a bacteria that is doubling. Yeah. Every hour, it's doubling. So it started with 500, the next hour it's 1,000, the next hour it's 2,000. With this pattern at 1 o'clock, what do you think it's going to be? 16,000. You double it again. "24 hours later, can you see that you could double it once for 1 hour later, then again, 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 then again. Can you see that writing all those times 2s could be a little bit annoying? How many times 2s do I have after 24 hours? 24 of them. Can you see that this would be a lot easier to write if I wrote it as 500 times 2 with the exponent 24, instead of having to write out all of those 2s every single time. So scientists like to write things out with exponents. And when they're dealing with numbers that are big like this, sometimes they would say, instead of writing 8.388, they round it and write 8.39, and they write it in scientific notation. Have you done scientific notation in science class? No. And in scientific notation, they say, instead of writing all of those numbers, we'll just write a couple of them, 8.39, and we'll say that this was times by 1, 2, 3, 4, 5, 6, 7, 8, 9. We move that decimal place 9 times. That's like multiplying by 10 to the exponent 9. And that's something called scientific notation. And our formula for this population, well, our bacteria, we started with 500. Then we multiplied by 2 to the exponent. I'm going to use the letter T. Is everybody okay with that? Where T is, I use T for time in hours. Can you see if the time was 1 hour, 2 to the exponent 1, we'd say multiply by 2 once. You'd get 1,000. If the time was 2 hours, 2 squared would be 4. 4 times 500 would give you 2,000. If the time was 3 hours, here we have 3 hours after. It's supposed to be 4,000. Look at the formula. If you put a 3 in there for 3 hours later, 2 times 2 times 2, that makes 8, times 500 would give you 4,000. So here we got another example of population. We start off with 100 mosquitoes, and these mosquitoes double every week. How many people actually wish there was mosquitoes outside right now? Would you trade the mosquitoes for the cold? Ooh, that's a tough question. No? Prefer the cold? Right? Can you imagine a place that has frozen mosquitoes? It's cold and you get bitten. And you know what's even worse? If you imagine this, you're like wearing a jacket, the only thing that's showing is your face. They would just go straight for your face the whole time. It just, bug spray, but it'd get in your eyes. Oh, it'd just be like, ah! Okay, sorry, my imagination's getting to me. We've got 100 mosquitoes, they double each week. How many mosquitoes would there be after 4 weeks? So we start off with, we start off with 400. Okay, we can make a chart here. No, we start off with 100, sorry. Our mosquitoes, after 1 week, how many mosquitoes are there going to be? They double every week. After 1 week, you would have 200. After 2 weeks, you would have 400, because it doubled again. After 3 weeks, 800. And after 4 weeks, 1,600. So I made a chart to do 1,600. Three months, there's 52 weeks in a year. 3 months is a quarter of a year. In 3 months, there will be 13 weeks. We could just keep going with our pattern. However, if we can make a formula for this, the number of mosquitoes started off with 100, it doubles every week. So we put time there in weeks. We can say it's going to double 13 times in 13 weeks. We can go to our calculator, type this in. Is this why we do have winter? So that mosquitoes that keep doubling all just sort of die off and we don't suffer worse and worse and worse? Wow. 819,200 mosquitoes. About how many weeks would it take to arrive to 12,800 mosquitoes? So this is our formula. And we need this number, the mosquitoes, to be 12,800. So what you could do is you could go to your calculator and try a value. So first of all, we know, does it make sense that your answer has to be less than 13? Because in 13 weeks, you're already at 819,000. So if you went to your calculator here and you said, I want to try something. 2 to the exponent, what number do you want to try first? Less than 13? 10. Okay? 10 is that number still too big or too small? Still too big. So we need to have something less than 10. Let's try something. Oh, perfect. So t is equal to 7. Yeah. All right, our next biology example. A patch of algae is found on the surface of Duncan, doubled in size each month. After 6 months, the algae covered the entire pond. How long? Oh, this is a good question. If it covered the whole thing in 6 months, and it's doubling every month, how long did it take to cover half of the pond? Okay? Yes, most common answer is 3 months, and 3 months is wrong. So, we need to think about this question, read it over a couple times, because this is something that if you understand exponents, you should be able to just tell me the answer. It is the most typical answer to say 3 months, and 3 months is wrong. Okay? It's doubling every month. In 6 months, it covers the whole thing. When and how long does it take to cover half of it? Okay? Okay, I'm going to, this is a good way. There. That is my pond. Oh, I like this. There's the pond. Here is month 6, month 5, month 4, month 3, month 2, month 1. All we know is that it's completely covered . There it is. The algae is covering the whole thing. This is the perfect use of crayons.
Oh, wow. How did I not go?
There we go. Month 6, it's completely covered in algae. It doubles every month.
Wait, why is there 2 here?
Oh, that is a good question. Why is there 2 2s? There we go. Month 1. If it doubled the next month, it would actually have to cover 2 ponds. Does that make sense? How if you work backwards? If you work backwards and it just doubled to fill the whole thing, what would it look like here?
Like probably just a quarter of it.
It's doubling. It would be half of it. How long did it take to cover half of it? 5 months. Got a couple more questions? Caden, do you need to be out in the hall? Because right now, both you and Logan are distracting other people in this class. So, I appreciate that, Logan. Okay. The frogs tripled each year. So, you start off with 100 frogs. You can make a chart for this as well and put years here. At the end of 1 year, how many frogs are there going to be? 300. It's tripling. At the end of 2 years, 900. You might have to get out your calculator. Wow. So we started off with our chart. What do we know that we're doing each time? We're multiplying by 3 because it's tripling every year. So our chart let us figure out 24,300. But if we wanted to figure out a formula for frogs, we've started off with 100, and then we have tripled for every year that we have. Right? At the end of 1 year, you've tripled once. At the end of 2 years, can you see you've multiplied by 3 twice? So that would be 3 squared. At the end of 3 years, you multiply by 3 times. So if you want to figure out 10 years, you could keep going with the chart, but recognizing the pattern makes it a lot quicker. How many frogs would there be in 50 years? Well, let's put these things into our calculator. Okay. At 10 years, 100 times 3 to the power 10. Wow. Almost 6 million frogs. And in 50 years, if this kept happening, my calculator gives my answer as a decimal. I'm going to just write the first 3. And then it says e to the 25. It's telling me scientific notation. So many frogs times 10 to the 25. Okay? If you want to know what 10 to the 25 means, that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That's an approximation. That's a lot of frogs.
Yeah, but how many would survive?
Well, that's just it. They'd probably run out of food. And you would probably, everywhere you would walk, there'd be frogs. Roads would get slippery. Ugh.